I want to explore a retrosynthesis of this molecule because there's lots of different types of heterocycle synthesis involved. This is risaxaban. It's a factor 10A inhibitor molecule that was developed by Bristol-Myers Squibb. I've put a link to the medicinal chemistry synthesis in the description below the video. There's a variety of different rings we need to deal with in this molecule. We have a benzisoxazole. That's this bicyclic one at the bottom left. Up in the top left, we have a pyrazole. There's just a normal substituted benzene in the middle. And over on the right, we have an imidazole. Now, each of those rings has its own chemistry associated with it. But to start with, the first sensible disconnection would be to cut right down the middle over this amide. That splits the molecule roughly in half, so we can make the two halves separately, and that will add a lot of convergency into our synthesis. It will also prevent us having to deal with any competing reactivity problems that might occur trying to build the molecule in a more linear way. So just the standard amide coupling should work there, going back to the acid chloride for the left-hand side, and coupling that directly with an amine. This coupling should have no problems. We have a primary amine, which will be reactive to the acid chloride. We might notice on the other side, we've got a tertiary amine, but if that nitrogen lone pair tries to attack the acid chloride, the nitrogen will just get kicked back out again. Now, an acid chloride can be made as and when we need it, directly from the parent carboxylic acid. For the molecule on the left, the acid chloride is the reactive part, so we need to disconnect that first. And you can make that simply just from the carboxylic acid using thionyl chloride. I'm just going to do that quick disconnection on the molecule itself. And now to go further with that molecule on the left, we need to think about what our next disconnection would be. We've got two heterocycles to make. It would be really great if we could do some sort of cut in the middle, again, to increase convergency. And to do this, we need to think about key strategies for making those two different ring systems. Just first taking a look at the pyrazole, I'm going to generalize it with just some R groups, just to focus in on the core structure. Now, one of the main rules in heterocycle synthesis, where you've got two electronegative atoms next to each other, is to avoid disconnecting the bond between them. That's because that bond-forming reaction is quite tricky, and there's only limited ways that we can do this. So it's best to focus on the other parts of the molecule. Ignoring the aromaticity, we can just look at isolated groups. At the top here, we have a CN double bond, which is essentially an imine. And how do we normally make imines? Well, we tend to go back to a carbonyl and condense on an amine. Another pattern inside here is an enamine. And, well, how do we make enamines? Well, exactly the same way that we'd make imines, except it's just a tautomer form. So we also need to go back to a carbonyl and condense on some sort of amine. And that gives us our key strategy. We're going to need carbonyls at these positions labeled with stars, which are 1,3 apart. So therefore, combining this logic, we need some sort of 1,3 dicarbonyl species, which is good because there's lots of ways of making those. So here we're going to need something like this, which we can get our R groups onto. So what do we need to condense onto it? Just going back to our pyrazole, we need the rest of the ring. So we need both those nitrogens and the R2 group. So essentially our disconnection will be across the ring like this with these orange lines. And the other component we need is this hydrazine. And this is where we start to encounter a regioselectivity issue. We need to make sure that each of the nitrogens ends up condensing on the correct centers on the other molecule. Now the nitrogen on the end of the hydrazine, even just sterically, is the most nucleophilic. But if our R2 group is aromatic, it could also be just a non-conjugated lone pair. So we need to make sure that we encourage it to attack position 1. If it attacks position 3 on the 1,3 dicarbonyl, we'll just get a different regioisomer of pyrazole. Worst case scenario, we don't even get the one that we want, or more likely we just get a horrible mixture that's very hard to separate. Neither of those options is okay. So we'll need to watch out for this when we do the disconnection. Now, I think using that sort of pyrazole chemistry is the sensible next thing to do for our molecule, because cutting across here does separate the molecule off into two big chunks. If I try to disconnect the benzisoxazole first, I'd only really be diddling at one end of the molecule and not really making much progress. So with our system at present, just looking at the hydrazine first, we have the most nucleophilic nitrogen at the end there. The other nitrogen lone pair is conjugated into a pi system, and so less available to be a nucleophile. But we have a big regioselectivity problem on our 1,3 dicarbonyl. In fact, it's a 1,3,4 tricarbonyl. Now, I'm not so worried about attacking at position 4. That's a carboxylic acid. They're not at all electrophilic at the carbonyl center, but the carbonyls at positions 1 and 3 are both the same functional group. They're both ketones. In fact, even worse than that, they're both electron-poor ketones in that they both have electron withdrawing groups on them, just abbreviated as EWG. So an alarm bell needs to go off. The hydrazine isn't going to be able to easily select for one of those in preference over the other. We're going to need to change this intermediate. It would also not be a good idea to have a carboxylic acid here either, because the first reaction that would happen would be that the hydrazine just picks off that proton. Now, we might say, okay, let's just protect that up as the ester, but that doesn't solve our regioselectivity problem at all. The carbonyls at 1 and 3 would still both be ketones with electron-poor systems nearby. Now, there's a very cunning trick that we can use in situations like this, and that is to do a functional group interconversion and completely change that carboxylic acid. And this functional group interconversion is to change the carboxylic acid into a furan ring. Now, it might not be completely obvious what we're doing here at first. The key idea is that this electron-rich heterocycle, the furan, can be oxidized to a carboxylic acid. In the forward sense, just in purple here, this is a known transformation. You need to use ruthenium trichloride in the presence of sodium periodate. These are strongly oxidizing conditions. It's a bit tricky to draw a legitimate mechanism on this, but this transformation has also been observed using ozone, so O3. One way of looking at this transformation is that it does exactly the same as an ozonolysis, as in these reagents just munch through all the double bonds and put oxygens in all the gaps. And then at some point, a hydrolysis occurs to leave this carboxylic acid behind. So just chomping off the free surplus to requirement carbons there. Now, why is this a useful transformation? Well, we've completely changed the game on our 1,3-dicarbonyl substrate. We now have the ketone at position 3 conjugated with this electron-rich ring system. That's going to make it much less electrophilic than the carbonyl on position 1. And so we've solved our regioselectivity problem for the formation of the pyrazole. If we mix these two things together and heat them up, we'll first get condensation of the terminal nitrogen of the hydrazine with the carbonyl at position 1 to first form this imine, which then can do an intramolecular condensation, maybe something like this, or via a tautomeric form. Most mechanism pathways will be available when we're heating these things up at quite high temperatures, to give us something like this, which by the loss of one proton can restore aromaticity and get to our product, which has all of the substituents in the correct positions. So we're good to go with this 1,3-dicarbonyl. We can make that using any old enolate chemistry, and we can address that in the forward synthesis later in this video. Okay, so this is looking good so far. All we need to do is make sure that we can make the hydrazine that's got our benzisoxazole ring attached to it. So just popping back to that intermediate in the middle in blue, the first thing we need to have a think about is, well, actually, it's got another amine on it that we didn't pay attention to before. This could also react with the 1,3-dicarbonyl. So things we might need to think about are, do we need to protect this? Or can we do something clever with the order of steps when we do a retrosynthesis? In terms of the hydrazine itself, there are classic ways of disconnecting these. The hydrazine can be made from the diazonium salts using some sort of reducing conditions. For example, we could use hydrogen gas and a palladium surface for this. And how do we make the diazonium itself? Well, this is some reasonably standard chemistry of amines and nitrous acid, that's HNO2. Nitrous acid is a pretty strong acid, and in equilibrium, one molecule might end up protonating another one to give me an intermediate like this, with a leaving group, to form the nitrosole cation, which can be attacked by our starting material amine, to give me this essentially oxidized hydrazine. With some proton transfers, we can get a double bond between the two nitrogens, and then finally an elimination of water by generating a leaving group and kicking it out to give us our diazonium species. So going back to our main synthesis, we need to consider how we might incorporate these sorts of steps. Just going to clear myself some space. And now we should just address how we might make the heterocycle, specifically with this amine substituent. Following the same rules as we had before, we've got two electronegative atoms stuck together, so we should try not to break this, as there are limited ways of joining those two atoms together. The thing that really stands out to me for this molecule is this carbon that I've highlighted with a red star. This is an oxidation level 3, or like the amide oxidation level. In fact, if we focused in on thinking about it like an amide, we can kind of see how we need to disconnect it. We have another CN double bond that we're going to need to make, and we know how to make those. And just as we did before, we can condense an amine onto a carbonyl there, or carbonyl-like species. And in fact, bearing in mind that there's two nitrogens there, a smart disconnection for something like that would realize that we could just use a nitrile instead, because an intramolecular cyclization should be pretty easy, and then we can just do a quick tautomerization into aromaticity. So bearing that in mind, we can use that to solve our chemoselectivity problem between the two amines. If I try to disconnect the hydrazine first, I get into a problem. I have two amines, both of which would react with nitrous acid and so I can't select the reaction to go at the correct position. So I'd need to factor in some sort of protecting group, all of a sudden sounding a bit of a pain. However, if I disconnect the benzisoxazole first, I don't run into the same issues. Now I can see here that I really can't avoid putting a protecting group on this nitrogen down here, but this really does give us quite a clue for how we can go forwards. At some point, we're going to need to think about attaching these things onto the benzene, and something is starting to stand out for me now. We have an electron withdrawing group with an ortho substituent. This is a pretty good signal that we might want to try using an SNAR reaction. That's a nucleophilic aromatic substitution to get one of our substituents on. Now we'll address the details in the forward synthesis, but now with that idea, we can really stack the deck in our favor by just doing a few functional group changes. To do the SNAR itself, I need a fluorine as my leaving group for substitution. But while we're here, if we know we're going to be using SNAR, we can make the ring even more electron poor to make this reaction even more easy. If we did a functional group into conversion to the nitro group there, because we know that we can reduce it later to an amine, we now have an excellent SNAR substrate. Both the nitro group and the cyano group are in the correct positions to store charge during that mechanism in the Meisenheimer intermediate. So I think this is a useful thing to head for. In terms of actually making this, well, lots of these things are commercially available anyway, but if we had to disconnect it, we need to take some of those substituents off. Now, putting fluorines onto aromatic systems use quite harsh reagents, so it's probably best not to disconnect off the fluorine first, because it would be nasty to put back on. So we've got a choice of whether we want to take the nitro group off or the nitrile. So there's disconnection 1, we'll take the nitro group off, or disconnection 2 is to deal with the cyano group. Going down option 1 would require this intermediate. The fluorine is paradirecting and the nitrile is metadirecting. So that's looking good if we wanted to use some sort of electrophilic nitrating reagent, such as the classic formation of a nitronium ion using nitric and sulfuric acids together. The slight issue with this is that these are both aqueous acids and both strong acids. They're going to hydrolyze the nitrile, probably to the carboxylic acid. Now, we could just deal with that and convert it back later, and that's all fine. But we could just have a quick look at the alternative disconnection 2. There are options here. We could put like a bromide or an iodide in this position, because using some copper chemistry, we can probably go backwards using copper cyanide here. That's just via the organometallic. Maybe slightly nasty to do on a large scale with your cyanide ion, but in any case, it's quite easy to make this substrate, as it would direct bromination ortho to the fluorine, with both the fluorine and the nitro group working together there to select that regioisomer. So we could just use some old-fashioned conditions for bromination there. And then a final disconnection would just be a standard nitration, the fluoride substituent directing para as normal. One way around using stoichiometric cyanide would just be to convert this bromide into the Grignard reagent and trap it out with carbon dioxide. That would give me this carboxylic acid. We could then convert the carboxylic acid to the amide and dehydrate it to the nitrile using POCl3. A bit steppy, but like I say, lots of different substituted benzenes are commercially available in the first place. So a lot of this work has been done by others already, possibly even just pharmaceutical companies selling off byproducts that they don't actually need. If you're enjoying the video, please do give it a like and share with any of your friends that might be interested. That really does help my channel find people who are learning chemistry at all different stages, and that means a lot to me. Okay, so that's the general idea for the left-hand fragment scoped out. Let's have a look at the right-hand one. It's a bit shorter, so I don't need so much space for this one. This fragment can just be made via a simple coupling between the two aromatic systems, specifically a disconnection here between the carbon and the nitrogen. This type of cross-coupling can be done quite easily between the aryl iodide on the left-hand side and this imidazole. Now I need to make sure this imidazole is in the presence of base so that it's deprotonated. But once you've got that, you can just do an Ullmann coupling, which is just heating these up in the presence of copper iodide. So a sensible base here for the imidazole might be something like potassium carbonate. Not something that's particularly sensible to draw a mechanism for. Copper's always a bit of a tricky one for things like this. These reactions are known not to go via radical-based mechanisms, but it's also quite unlikely that they go through some sort of species that contains copper in the +3 oxidation state. That's because copper +3 attached to an aromatic system, for example, after oxidative addition into the carbon iodide bond, the copper +3 is not particularly stable when bonded to a carbon, particularly one with a pi system on it. The electrode potentials show that this sort of bonding interaction is not particularly stable, but unfortunately you do still hear organic chemists talking about this sort of species every so often, but it's more of a church or a belief system rather than anything that there's evidence for. The imidazole component, it's just got an amine dangling off it, so we can disconnect that in a standard way by reductive amination to give us something like this. This imidazole aldehyde is actually readily available. If you did find yourself having to make it, you'd probably want to use chemistry something along this lines. Provided you've got a protecting group, some sort of R group on the nitrogen, the proton I've highlighted in green is the most acidic. If you treated this with a strong base, such as butyl lithium, you could deprotonate that to give you the nucleophile, and then reacting that nucleophile with something like DMF should give you the aldehyde that you need after you've taken the protecting group off. For the remaining aromatic fragments, we just need to get that iodine on. Now, iodination of benzene rings can be notoriously difficult. It turns out that this substitution pattern is actually readily available, but should we want to try and disconnect it, we probably want to do something along the lines of putting the iodine on from this sort of intermediate and hope that the nitrogen lone pair is a better donating group than the fluorine, which I think is reasonable based on it having a lower Z effective, so its lone pair is higher in energy. We can't just use elemental iodine as the reagent for this sort of thing. You normally need to use it in the presence of copper. That's partly because the electrophilic substitution mechanism tends to set up an equilibrium if the copper salt isn't there and prevents you getting to the product. You might need some extra copper chloride in there, just in case some of it coordinates up to the amine. But the reaction is probably tolerant of it being a free amine. If you had problems, of course, you could protect it up, I guess, with an acetyl group, which you could then hydrolyze off later. Or if you're having real trouble with the direct iodination, there's no reason why you couldn't just brominate and then use an organometallic to get the iodide on. The iodide's quite important for a reliable Ullmann coupling, so I don't think we can skimp on that one. I'm sure there are other workarounds in the literature if there was a problem here. Okay, so tying this all together, we just need to be a little careful on our order of steps, but I've worked through the key ideas. I talked about this intermediate being quite a good SNAR substrate. The top bit needs to go to a hydrazine, and this bottom bit becomes benzisoxazole. If we make the benzisoxazole first, at some point pretty soon, we're going to end up with two amines, which we won't be able to differentiate easily. Now, we could use protecting groups, but on reassessment of this molecule, the nitrile and the fluoride are doing a quite good job of protecting that part of the molecule anyway. They're pretty inert through many of the other steps that we need to do, so it might just be best to keep them there for a while and put the benzisoxazole in right at the very end. So first we've got to reduce that nitro group to the amine. Now we need to be a tad careful here on our reagent choice. We can use tin dichloride to do this. One thing we can't do is a catalyzed hydrogenation because the nitrile would also be hydrogenated as well. That would take the nitrile down to an aliphatic amine that we don't want. Next, we need to convert that amine to the hydrazine. Now for this, we need some sort of reagent that generates nitrous acid or nitrous acid itself. So let's just go with that. HNO2 will form the diazonium species, and then we just need to reduce it down to the hydrazine. We can just use tin dichloride again for that. Next, we can construct our pyrazole. We just need our 1,3-dicarbonyl there. To get the condensations with the amine, we normally use catalytic acid, and we should probably heat that to drive the reaction forward to aromaticity. You can drive the water byproduct off this way too. Just while we're there, that dicarbonyl could be made by enolate chemistry if we use this furyl methyl ketone, which is readily available. If we treated that with a base, say sodium methoxide, we could generate the enolate by deprotonating the only acidic proton, and then we could trap out the enolate with something like this electrophilic ester. The 1,3-dicarbonyl product will be deprotonated under those conditions, so we should favor a mono addition, as the final product can also be deprotonated, form a very stable anion until workup, and help push any equilibrium towards the product that we want. Okay, next it's time to use our cunning trick. We can oxidize the furan into the carboxylic acid, and then we actually need the acid chloride for future reactions. So as a second step, we can just put in thionyl chloride. To give us this coupling partner we need for forming an amide with the other fragment. Talking of which, what we needed to do was an Ullmann coupling between these two aromatic intermediates. So that's using copper iodide, and we need to deprotonate the imidazole too. So potassium carbonate will do that. And that gives this intermediate. Next thing we need to do is expose this amine to the acid chloride. Probably sensible to do this in the presence of pyridine. And that's our key fragment coupling to form the linking amide. And now all we need to do is make the benzisoxazole. Now the plan was to use some sort of SNAR chemistry. We can't just use hydroxylamine on its own because as is, the nitrogen is more nucleophilic and we need the oxygen to substitute for the fluorine and attach itself to the ring. So we can temporarily mask the nitrogen and use a slightly different starting material, just masking it as the acetamide. And then we have an acidic proton on the end. So provided we add a sensible base, we can deprotonate that and make the O- nucleophile. Let's just use potassium carbonate again. So the idea in this step is that we get SNAR, where first we attack where that fluoride is encouraging us to. We can delocalize the electrons up to the nitrogen, and then they can come back down again and kick out the fluoride leaving group. Now, I think these basic reaction conditions actually allow us to go a bit further. We have quite an acidic proton there as part of this amide type functional group. Every possibility that that gets deprotonated in the presence of potassium carbonate, and there's a driving force for a further reaction where we can cyclase. This intermediate has a very labile acetyl group on it, because if we do some proton transfers, it could be hydrolyzed to push towards an aromatic product. This potentially could happen during the reaction or maybe even on some sort of acidic workup. Firstly, we would quench that negative charge with a proton, hydrolyze off the amide, and then you have your product, which looks like this. If you enjoyed this synthesis discussion, you can find others on my channel. YouTube is just picking a couple for you now on the screen that you might be interested in.